All right, so I want to remind you, when is your exam? 13th, Tuesday, the 13th at 11 o'clock. Where? Here. Okay, so just let you know. It is in here at 11 o'clock on Thursday. It's a 2.5-hour exam. So you will be done with the exam by 1:30. So from 11 to 1:30 in here on the 13th. Just let you guys know. All right, in case you need a reminding. If you do need more reminding, on your Canvas page, it's down here at the bottom. It says, 100 points, December 13th at 11 a.m. All right? So, today I thought we would sit there and go over some of the old tests and stuff like that and kind of get you prepared for what you anticipate on the exam. Question?
So can we ask anything on like previous tests that we like didn't understand?
Of course. That's what I do. That's what I'm going to sit there. I brought a version A, so there's version B will be similar, but yeah, maybe different and whatever. But yeah, I brought a copy, blank copies of the exams that we can actually look at and stuff like that. And I can tell you, yeah, you need to study this. No, don't worry about this, okay? So, again, I want to kind of focus on that. So the first thing I want to focus on, and I'm going to start with test number 3, and then I'll work back to test 1 and test 2, only because test 3 is the most recent thing in your mind. And the one thing that's going to definitely be on your test is definitions. So I sent everybody a copy because I was afraid what was going to happen, and it ended up happening. I sent everybody a copy of this thing through Canvas email saying, you need to study these definitions. And because what I didn't want is these made-up versions of the definitions. I wanted something more realistic of what the definitions are. And some folks decided, no, they like their own made-up version of the definition, which wasn't quite accurate as it needed to be. So, study these definitions. You check your email box. This thing is actually in your email box. So not only do you have to copy it down, you actually have I have the original here. You got a scanned copy of exactly this. So what exactly are eigenvectors and eigenvalues of a matrix? The eigenvalues are the constants lambda, and the eigenvectors are the vectors v, where you have a square matrix A has the property, and this is what I was looking for, A times V is equal to lambda times V. A matrix acts on a vector like a constant. Scaling it acts on a vector. That is what an eigenvector and eigenvalue are. It's a very special scenario where matrices literally actually act like constants. Column space, the column space of a matrix A is the span of the column, keyword here, vectors of the matrix. You look at the columns as vectors, and it's the span of those vectors that creates a space. There's another word I want to focus on again because I saw a little bit of a problem with this on the test. If I ask for a basis, all you have to do is list down the vectors themselves. If I ask what is the space of whatever, obviously you still need the basis, but if I ask for the space, what do you have to tell me? It's the span of the basis. And you write the word span in front of it. Span being by definition all the linear combinations of the basis elements. Okay, so I had a few folks sit there, what is the null space? And they just wrote the basis down. Okay? Oh, well, great. You need the basis. That you only got a Wiener point taken off, but you needed to write the word span in front of it because the span actually creates the space. All right, so continue on. So when we're talking about the column space, it's the span of the column vector. So notice I'm using the word span there. What is a basis? A basis of a vector space is the set of vectors B1 through Bn that are two things. They are linearly independent. I'm looking for that word. And they actually span the vector space. So when I put the word span in front of them, all the linear combinations will get any vector in that vector space will be a linear combination of those basis elements. Dimension of a space. Now this was important. The dimension of a space is the number of vectors in the basis of that space. So, real simple. The number of vectors in the basis. That's all I was looking for. I got some interesting concepts on that one, and not quite accurate, but okay. Linearly independence. A set of vectors, V1 through Vn, and this is actually from chapter, 3, 2. A set of vectors V1 through Vn are linearly independent when you set C1 times V1 plus C2 times V2 plus dot dot plus Cn times Vn equals 0 implies that the only solution is C1 equals 0, C2 equals 0, C3, dot dot dot, Cn equals 0. That's the only answer you get. It's called the trivial answer. Okay? Null space. The null space of a matrix A, the null space of a matrix A is the span of the vector solutions of the equation AX equals 0. So, another word for AX equals 0 is also known as the homogeneous. Remember those words? I can throw that kind of stuff at you as well. So go back and look at some of the old definitions like homogeneous solutions of a system of equations. Okay, so you're setting the system variables equal to 0. All right, and then the last thing is, what is a vector space? This was our definition. It's a three-parter definition. A subspace W of a vector space B is a vector space if 1, the 0 vectors inside of W, 2, if V and W are vectors inside of W, then V plus W is an element inside of W, and 3, if C is an element of R, the real numbers, that's your scalar, and V is in W, then C times V is an element of W. So you've got scalar multiplication, you've got closure under vector addition, and you've got the 0 vector has to be inside your set. Those three things is what makes a quote-unquote vector space, a vector subspace. Okay? It's three things you have to check. Or you could do something like this. If I have to prove a vector subspace, as long as I can write it, the vector subspace, as a span of a set of vectors, I win the game. Because we proved in our theorems that we've been proving in this class that the span of any set of vectors makes a vector space. All right. Based upon that, I'm going to look at your test number 3. I got version A up here because I didn't want to bounce between A and B because they're going to be very, very similar. All I did was change some other stuff up here. Okay? One of the first problems that I saw on the test in terms of, consistent bonehead mistakes was number 2. So I want to take a look at number 2 here. Okay? It says, use the definition of subspace to determine if H is equal to 2AT minus 5BT cubed, where A and B are real numbers, is a vector space of P3, the set of polynomials of degree 3. But then I gave you guys a hint. Here's what I really wanted you guys to use. Think about theorems. You got definitions, but you also got theorems. Theorems about the span, and remember a vector A0 plus A1t plus A2t squared plus A3t cubed, degree 3 polynomial, is isomorphic to the, and you can write it as a classic vector in R4, A0, A1, A2, A3. That's a vector in R4. All right, so here's what you need to know. Okay, so I'm going to write it the way I actually put it on the little thing here. All right. As H is equal to this set here, 2AT minus 5BT cubed, such that A and B are elements of the reals, okay? Then H would be equal to, in terms of this, here's my hint right here, I'm taking this polynomial and writing it as a, because it's isomorphic, is equal to this vector of, there is 0 constant, there's a t here, so this would be 2a in the second spot. The third spot is the squared, there is no squared, and the last spot is the a3, that's the t cubed, we got a negative 5bt cubed, that's negative 5b. All I did was rewrite the polynomial in this isomorphic vector form, okay? For A and B being real numbers. Thus, H is actually equal to the vector 0, 2, oops, sorry about that, 0, 2, 0, 0 times A plus 0, 0, 0, negative 5 times B. What did I do from this step to this step right here? What did I do? constants, the A and the B, right. But there's two of them, so I've got to separate the A ones from the B ones. So I took this guy up, there's 0 and 0, so the first component is 0, the third component is 0, but the second component is a 2A, and then the fourth component is a negative 5B, so I have to separate that. There's my 2A, there's my negative 5B, okay? Again, where A and B are real numbers, okay? Hence, H is actually equal to the span of the set of vectors 0, 2, 0, 0, and the vector 0, 0, 0, negative 5, right? Thus, by theorem, H is a subspace of, why is it a subspace? Because I wrote H as a span of a set of vectors. That was our theorem. Now I can go back and look at the definition and I can show you if A equals 0 and B equals 0, then the 0 vectors inside this thing. If I have two vectors looking exactly like 0, 2A and 0, negative 5B, you can call A1 and B1 and A2, B2, add them together. You can factor it out and get the same format. And if I multiply it by a scalar constant, I can pull out that constant or put it inside there and it's still going to have that same format. I could use the definition. It's a lot more work. But remember, if I can write your vector, your subset as a span of a set of vectors, that automatically makes it a vector subspace. Does that make sense? And that was really what I was looking for. And that was a problem we did actually on the homework, number 6 or whatever it was. Okay? Does that make sense? There's one other one that I want to look at with you guys before I actually just open it up for questions and stuff, is this. All right, let's see here. Which are some other ones that I actually saw here? All right, so for example, number 3. I think number 3 was connected to the aspect of number 2 there. All right. Let W be a vector space. W is equal to this big vector with the A, B, C combinations here. A, B, and C are real numbers. Find a basis for this guy. It looks exactly like the other one. The other one I just did was a polynomial, but I had to rewrite the polynomial in terms of the t and the t squared and t cubed as this R4 vector as we were just talking about. This guy right here, well, I'm going to rewrite W. And I said, you may use your calculator to check for linearly independent. So you want to make sure you have a basis here. So this is what I was after. So W would be equal to, if you rewrite this guy, okay, it's going to be equal to, I'll just do it this way, big old bracket here. It's going to be, look at the A's. And I really tried to help you guys out because I wrote them in order. If you notice some of that homework stuff you do online, you don't ever write that stuff in order. So you have to redo it. This one I put in order. So here's the A's. It is 1, 2, negative 1, 3. That part's times A. Plus the next one is the B. It's negative 2, 5, negative 4, 1 times B. Plus the guy C was 5, negative 8. That's a negative right there. Negative 8, 7, 1 times C. I just rewrote my one big vector as a linear combination of these little vectors. You with me? So right here, this guy makes W a subspace. Does that make sense? W is a subspace. Okay? And it would be a subspace of actually R4. That's where the components are coming from. Four components. Does that make sense? However, one of our big definitions is this. To have a basis. Now I got a spanning set right here, but I don't know if it's a basis. Bases have to be what? Linearly independent. And I gave you a hint on this linearly independent thing here. So if I write this guy as a matrix, column matrix, 1, 2, negative 1, 3, negative 2, 5, negative 4, 1, and 5, negative 8, 7, 1. Okay? I want to do reduced row echelon form. Now I had a couple people in here who said, wait a minute, when I put this on my calculator, it gave me the famous dimension mix match error message, right? So what do I have to do? The problem is, you got 4 rows, but you only have 3 columns. You gotta have at least the same number of rows as columns. So what did you do to actually get it on your calculator? Just put a row of zeros in there, the zero vector, 0, 0, 0. No one can put it as many 0 columns as you want on this thing. All you need is 1 more. But when you do that in reduced row echelon format, you get this. 1, 0, 1, 0, 1, negative 2, 0, 0, 0, 0, 0, 0. This is the reduced row echelon form. The reduced row echelon form is gonna tell me something or other. What is it telling me? I'm looking for, is this, these set of vectors, is it linearly independent or linearly dependent? Tell me. Linearly what? Dependent. How do you know? You got one free variable. You got a pivot in the first column. You got a pivot in the second column. This third column is not a pivot, which means it's going to be a free variable. But in terms of the basis, to write it as a basis because it's linearly dependent here, LD, that's that linearly dependent code that I came up with, dependent, okay? So it's linearly dependent, which means I only need the 2 vectors. What 2 vectors to actually make a basis here? And that would be the first and the second one. So it'll be the vector 1, 2, negative 1, 3, and the vector negative 2, 5, negative 4, 1. Those are the ones that are actually the basis. And so there's my answer right there. The basis for W are these 2 sets of vectors. Does that make sense? How do I know I have a basis? I gotta be linearly independent. Okay. All right, this one I tried to make real quick for you guys, but I see some people messed it up because you forgot your formula. All right, we were trying to find these transition matrix here, these coordinate matrices, the change of coordinate matrix. So given that B and C are basis, and notice I use the ES word because there's 2 of them, so that's plural, basis of R2. You may use your calculator to find the change of coordinate basis from B to C and then from C to B. Make sure you label which one's which. So here was the formula. If you want to go, P being the change of coordinate matrix, from C to B. Now we had this notation for a reason, and I kind of went over that notation of you're going from C, follow the arrow, to B. This is changing it from C to B. The reason why we write that as a matrix is because you put your B columns on the left, B1, B2 as vector columns here. You augment that with C1, C2, okay? And I'll go ahead and do that because this will be 1, 1, 2, negative 1. C1 was 4 1 column vectors and 7, negative 2. And then what you do here is you should reduce row echelon format. Of course, this guy on the left should show up as an identity. If it's a basis, they should be linearly independent. So you get the 1, 0, 0, 1. But then you augment, and here it is right here, you get the vector 2, 1, 1, 3. And this goes to the identity, and this part right here becomes the P going from B to C. This is how you get it. B on the left, C on the right, reduced row echelon form. You get identity on the left. This P matrix here, P going from B, so excuse me, I made a mistake there, it's C to B. I read it backwards, my fault. This is going from C to B. C to B becomes the matrix 2, 1, 1, 3. Okay? And now all I got to do is basically the inverse of this guy. If I want to go from B, from P matrix, from coordinates from B to C, but since you got to do the inverse anyway, you might as well do it this way. Put the C1, C2 here, the B1, B2. This time the C's on the left, the B's on the right. So this will be 4, 7, 1, negative 2, and this B1 would be 1, 1 there, 2, negative 1. Again, reduce row echelon forming it. This will show up as the identity, and this becomes your transition coordinate matrix. But this one time it's going from B to C, and yeah, I got 3/5, negative 1/5, negative 1/5, and that was 2/5. So this P transitioning from, this one was from B to C, This one's gonna go from C back to B, which is just the inverse, by the way. This is 3/5, -1/5, -1/5, 2/5, and half the people wrote it as a decimal, which is fine. 0.6, -0.2, -0.2, 0.4. I took it either way. Does that make sense? And remember, what this does is this the matrix, it changes the coordinates of writing it in terms of basis, in this case, basis B1 to try to, it tells you what the coordinates would be in terms of the new basis C1 and C2. So this is your transition, and that's taking these coordinates from one set of coordinates on a basis to another set of coordinates on a different basis. All right, the other one that people just cried about points was, this one was good, this one was good. I'll look at this one, number 6, because you're gonna see number 6 again, but the one that I wanna look at that people just really just died on was, it's so sad, number 7 part A, and then they died on 7 part B, because if you couldn't get part A, well then you're gonna die on part B. All right, now, let's consider the vector space P5. What is P5? Well, P stands for polynomials of at most degree 5. What is the standard basis for a polynomial? Okay, well, no, I didn't ask for what the dimension is. We'll get there in just a second. And you're right. What is the basis elements for a polynomial? Well, for a polynomial, you can have a constant. You can have first power, a t squared, a t cubed, a t to the 4th, a t to the 5th. But wait a minute, this is P5, so you get to stop at t to the 5th. This is your basis. I didn't ask for what was it isomorphic to, because that's what most people who messed it up gave me. They gave me 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0. They're putting the ones in terms of, they're trying to do what we did in the previous problem with the polynomials and writing it as a column vector. Now, I didn't ask for that. I just asked for the basis elements. Yes, you're right. It's isomorphic to what you gave me, but it wasn't the standard basis of the P5. This is a polynomial, so I need polynomial terms, constant. T squared, t cubed, t to the 4th, t to the 5th. I gotta have some polynomials in there to be a basis. Does that make sense? Now, I saw some people die on this one, and I have no idea. What's the dimension? That's correct. Why?
6
There are 6 6 vectors and polynomial vectors, polynomials in the basis. 1, 2, 3, 4, 5, 6. And it threw people off. How can it be P5? Because you got t to the 1st, t squared, all the way up. But you also forget you can have a constant. And because of that constant, it added one more dimension on it. That's where the 6 comes from. Does that make sense? I saw interesting answers from 4 to 6. Okay, I did get some 6 people in there. But a lot of folks put 5 on there because I guess P5, because you're thinking R. What's the dimension of R4? 4. And they get that theory in their head. And then, okay, but that's a different kind of vector set. So there you go. Okay? But when you want to start manipulating these guys, down here, this is when you want to actually start rewriting these guys in column vectors based on their coefficients of the standard basis, so you can actually start putting them on your calculator and manipulating them and stuff like that. So, with, in terms of this one right here for part C, since I'm doing it, you can rewrite this as a vector. 1, t squared, t cubed, t to the 4th, and t to the 5th. So this becomes, this implies beta ends up becoming this vector here. When you look at this first one, it's the constant is 2. You got a minus t squared, so there's no t. There's a negative 1 t squared. There is no t to the 4th, but there's a 1 t to the 5th. And there is your vector there. Oh, wait a minute. There's no t cubed. Lost a t cubed there. T cubed and t to the 4th. There's none of those there. So, sorry about that. How many components? 1, 2, 3, 4, 5, 6. Now I feel better about myself. Okay? And then the next vector, this guy here is t plus t4 t to the cube. There's no constant, there's one t, there's no squared, there's a cube, that's a 4, there's no fourth, and there's no fifth. There, get my vector there. And so the next vector would be this 1 plus t minus 3t cubed plus 4 t, 2t to the fourth. You got almost all of them. You got 1, you got a no t squared, right? You got a negative 3, you get a 2, but there is no t to the fifth in this guy. Did I skip one? Yeah, I did. I skipped this guy here, sorry about that. I got a negative t plus 2t to the fourth. I got a 0, negative 1t, no squared, no cubed, a 2t to the fourth, and a no t to the fifth. Sorry about that. Switch the position of those two guys up there. Okay? And then these last two are 3. Excuse me, this one here. I'm going to miss them. 0, 0, constant, 0t. There is a 1t squared, a negative 1t cubed, no t to the fourth, no t to the fifth. Okay? And then we got this last one right here, which is 3, 1, negative 1, constant t squared, t cubed is negative 3, t to the fourth is 2, t to the fifth is 1. This is the one you actually got a number in each column, little component there. So this is what we're looking at in terms of being. And I checked, you got six vectors here. Just remind you, the dimension of P, what's this, 5, was equal to 6. So I got the correct number of vectors. But how do I know this thing's going to be a basis? And is it a basis or not? What do I do? Augment it, make one big matrix. 2, 0, negative 1, 0, 0, 1, 0, 1, 0, 4, 0, 0, 1, 1, 0, negative 3, 2, 0, 0, negative 1, 0, 0, 2, 0, and 0, 0, 1, negative 1, 0, 0, and 3, 1, negative 1, negative 3, 2, 1. And you may use your calculator to help, but you're going to RREF this guy. But what do you get when you RREF it? You get 1 and a bunch of zeros below that. I think there's like 6 of them. 1, 2, 3, 4, 5, 6. And you get 0, 1, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 1, 0. But then on the last one you get 1, 0, 0, 1, 0, 0. How many pivots did you actually get? Pivot, 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 pivot. What's this dude over here? Free variable. Okay? So, question. Is this thing a basis for P5? Well, because it's a free variable, this is linearly dependent, so you got really a linearly dependent set. So, and you needed 6 of them, but they got to be linearly independent. These are linearly dependent, so the answer is no. Set of beta vectors are linearly dependent was the answer that I was looking for in terms of this kind of a problem. Does that make sense? So, again, looking at the relationship between these guys and stuff like that. Alrighty, so, yeah.
So for the final answer, is it like each one of them has to be, you have to check each one of them is linearly independent, or can like?
Well, you check a set of vectors if they're linearly independent. And what you do is you write them in terms of a, isomorphic 2, since these guys were originally polynomials or whatever, but you get them into what we call column vectors. And then I reduce row echelon format, and then I look at the pivots. If every one of the vectors that I had in my set is a pivot, then it's going to form a basis, provided the dimension, the number of vectors in that set is correct. I did have 6 vectors, so that was correct, but they had to be linearly independent. Because P5 is 6-dimensional, it's got six basis elements in there. And so this one was, the number of vectors is right, they weren't linearly independent, is the problem. They gotta be linearly independent, part of that definition, linearly independent, and you gotta have the right number of vectors.
So each vector has to be linearly independent, you can't have, since there's like.
Right, no free variables. Can't,
There's like 6 vectors here, you cannot have, like, one of them be.
right, right. Cannot, because P5 has to be 6, so I have to have 6 vectors in my basis. And this thing right telling me is, the first 5 are good, and the last one's the problem. It's not, that one's linearly dependent by the other guys. Those were the big ones that people made some bonehead mistakes on and stuff like that. So, since I am actually doing most of the test, and this is a good test, you definitely want to go back and review on. Are there any other questions that you want to actually for me to take a look at? Now, if you look at number 8, this is some of our big point totals and stuff. And again, let me start with number 6 first. Number 6 here. Okay? Number 6. This one is one that we have done since test 2. Actually, yeah, really focus on chapter 3 and chapter 4 stuff right there. So, question for you guys here. All right. This right here, I want to emphasize this because it's free point, but people are just dying on the free point stuff. I gave you, and this is what I plan on doing on the final exam, I gave you a matrix. There it is. Okay? This thing happens to be, let's see here, 1, 2, 3, 4, 5 by 1, 2, 3, 4, 5, 6. 5 by 6. Okay? And I gave you its reduced row echelon form equivalence, just to save you guys some time. Okay, you could put it on your calculator, but that takes some time just to type it all in and make sure you didn't screw it up. So I went ahead and gave you that to you. If I'm asking for what exactly is the column space of this game, column of A, I want to know, well, basically, it's the span, because it's a space, of a set of vectors. Which vectors? The pivots. Where are the pivots located at? First column, second column, and third column. The rest of the, and wait a minute, and fifth column. 1, 2, 3, first, second, third, and the fifth column. Does that make sense? These are your pivots. Ones with zeros above and below, which means my column space is going to be the span, because it's the space, of the basis. And that's what I was after. This was the basis, but because I asked for column space, you need to put span in front of it. And because this is reduced row echelon form, I got to go back to the original matrix, which was 1, 2, 3, 1, 1. 1, 4, -3, -3, -1. -3, 8, -3, 1, 0. And then the fifth column, 1, 2, 3, 4, 5, 9, 26, 3, -8, -5. All right. Here's another definition. What's the rank of A? What's the definition of rank? The dimension of the column space. Definitions you need to know. Rank is the definition of the column space. Well, you just wrote the column space as a span of a set of basis vectors. How many basis vectors were there? 1, 2, 3, 4. Does that make sense? This is again where I saw some people screw up. All I need, dimension. Rank is a fancy word for the dimension of the column space, and it's the number of vectors in the basis. That's the definition of dimension. But column space is a subspace of RK. What would that be? That means the RK thing it's a subspace of is how many components in the vectors. How many 1, 2, 3, 4, 5. Does that make sense? So 5, because each one of these vectors comes from R5. Now, this one, you had to do the row space, and then I asked for basically what is the standard basis, and I could do that on this one. What is the standard basis of the row space, okay? Well, here's the deal. When you went from this matrix to this matrix, what method did you use? You used reduced row echelon form, right? So with that, to go for the standard basis, you gotta have I can either use these guys over here where the pivots are located at, or because it's reduced echelon form, I could use these guys. If I want the standard basis is the basis that has the most zero components in it. So this would be the ones I use. It would be the span of the set of vectors. The first vector is the 1, 0, 0, 2, 0, 2. The next one is the vector 0, 1, 0, 2, 0, 1. Let's see, the third vector, because I have a room here, is going to be 0, 0, 1, negative 1, 0, 4. And then I had 4 vectors, which is where this guy is at. This guy has a component, which would be the 0, 0, 0, 4, 0, 0, 1, 0. And there it is. And I put little pointy brackets around there because that's a Calc 3 notation thing here. I would have taken brackets or anything, but you got to give me just the rows. Does that make sense? Yeah. Well, let's see here. What did I actually put in here in terms of this one? Find the standard basis for the row space. So I had to use B. Okay? Yeah.
How did you get 5 for because call A is subspace of the
Okay. So look at one of the basis vectors. How many components are in there? That's why it's an R5. So that K is how many components are in your vector. That's where you're a subspace of RK. But then the dimension of the column space, these are the 4 vectors in the column space, and so dimension is going to be 4, because there are 4 vectors in the basis. Now the null space is the one that you actually had to work on and stuff like that. And what is the null space? So all this. Did I actually do any work except use what I gave you guys on the first 2? All the work is on the null space. Remember, the null space is where this AX is equal to 0, okay? So you can augment this thing with 0, and then you're going to reduce echelon form. So this would be equivalent to saying this vector, 1, 0, 0, 2, 0, 2, 0, 1, 0, 2, 0, 1, 0, 0, 1, negative 104, 0, 0, 0, 0, 1, 0, and then a row of zeros, times basically your x1, x2, x3, x4. How many? 1, 2, 3, 4, 5, 6. x5, x6 is equal to the 0 vector. So this is, what do we got here? 5 by 6. So 5 by 6 times a 6 by 1 would be a 5 by 1. 1, 2, 3, 4, 5 zeros. Does that make sense? But then you write them back as equations, and you solve for the pivots. So this represents the x1, x2, x3 stuff here. So you end up getting x1 plus 2x4 plus 2x6 equals 0. x2 plus 2x4 plus x6 equals 0. x3 minus x4 plus 4x6 equals 0. And x5 equals 0 from these 4 equations here. But remember to solve for the null space, you solve for the pivots. The pivots are x1, x2, x3, and x5. So x1, x2, x3, and x5 equals, okay, x1, when you move this to the side, is going to be negative 2x4 minus 2x6. x2 is going to be negative 2x4 minus x6. x3 is going to be x4 minus 4x6. And x5 is equal to 0. And then we got, let's see here, we got 6 components here. Here's x6 and here's x4. x4 and x6 are your free variables. Free variables are what? Equal to themselves. I'm trying to line this thing up for you guys. So this tells me right here, I end up getting x1, x2, x3, x4, x5, x6 is equal to -2, -2, 1, 1, 0, 0 times x4 plus -2, -1, -4, 0, 0, 1 for the x6 times x6. So with that, what is the null space? It's a space, so we're going to use the word span of these set of vectors. -2, -2, 1, 1, 0, 0. Okay? And -2, -1, -4, 0, 0, 1. Here we go. What is the nullity? What does the word nullity mean? What's the fancy word for nullity? Nullity of A, matrix A, is the dimension of the null space. That's your definition of nullity. What's that? 2, because I got 2 vectors in the basis. But the null of A, null space of A, is a subspace of RK. What would K be here? What kind of components I got on these vectors? 1, 2, 3, 4, 5, 6. So K would be 6. Does that make sense? Okay. Again, focus on this one. The other big one that had some major point totals on it was this guy here. And I am spending a lot more time on test number 3 because if you haven't figured out how the linear algebra class works, we kind of been building up to all the stuff we're doing in this guy here. So, and I'll talk about what I plan on doing in terms of the test. You know, and I try to give something nice to you guys because you only had like 75 minutes for the test. So I gave you guys a 2x2 matrix. I reserve the right to give 3x3 matrices. That'll be the worst I give you is a 3x3 when I ask for eigenvectors and eigenvalues, okay? But don't forget, you can use your calculator to find these eigenvectors because you take your determinant and you set it equal to 0, the determinant of A minus lambda I. You set it equal to 0, and if it's a nasty looking guy, graph him, and where it crosses or touches the x-axis, those become your eigenvalues, okay? Classic polynomial stuff here. But this one, I tried to make it real nice for you guys because I was trying to make a short test, but it doesn't really matter. You guys just don't care about me doing short tests in here. You're just going to take as much time as humanly possible. So here we go. Characteristic equation. What is it? It's the determinant of A minus lambda I. Okay, and you set it equal to 0. This would be the determinant of A, which is 4, -3, 2, -1, minus lambda times I, 1, 0, 0, 1, the identity. Okay, equal to 0. Well, this pretty much becomes the determinant of 4 minus lambda, -3, 2, and then -1 minus lambda, okay, equal to 0. And you end up getting your equation, but you do have to manipulate the algebra. How do you take a determinant of a 2x2? Main diagonal minus off diagonal. So that's 4 minus lambda times -1 minus lambda minus -3 times 2 equal to 0. Now, where I saw some people during the test die on this one is their inability to actually multiply numbers and lose signs. This class is called linear algebra. You imagine what happens to you if you cannot multiply and or subtract or add. You'd crash and burn all over the place. And honestly, my friends, when I was taking this class years ago, the ones that did poorly on the class are the ones that made bonehead careless errors because they couldn't add or subtract. So be careful. Take your time. You actually have to FOIL this out. That gives you -4 minus 4 lambda, minus lambda times a minus 1 becomes a plus lambda. Watch your signs. Minus lambda times a minus lambda is a plus lambda squared. And this is -3 times a negative times a positive 2, which is a -6, but minus a -6 makes it +6, equal to 0. Okay? When you clean this up, you end up getting lambda squared. And then combine your lambdas. I've got minus 4 lambda plus lambda is a minus 3 lambda. And then I got a minus 4 with a plus 6 makes it plus 2 equals 0. You should be grateful for this. I didn't make you do any weird quadratic formula or anything. This guy factors. Lambda minus 2 times lambda minus 1 equals 0. And you end up getting lambda equals 2 when you set that factor equals 0. And lambda equals 1 when you set that factor equals 0. Okay? So automatically, they ask for the characteristic equation. I was looking for this. Lambda squared minus 3 lambda plus 2. It's an equation, so don't forget to set it equal to 0. Okay? You could have also given me the factored version of it, and I would have accepted that. My eigenvalues are lambda equals 1 and lambda equals 2, 1 and 2. What about the eigenvectors? Okay? So you go back up here and you go lambda equals, let's say, 2. And you plug it into this A minus lambda I. You end up getting a matrix, and here is the matrix right here. 4 minus 2, which is 2, negative 3. This is 2, and negative 1 minus 2 is negative 3. Okay? And basically, to get the eigenvector, you multiply it times v1, v2, and it's equal to 0, 0. Okay? But what you really do is you're going to take this 2, negative 3, 2, negative 3, augment it with 0. You really want to put the zeros on there. Reduce row echelon form it. That gives you 1, negative 3 halves, 0, 0, augment it with 0, 0. And you're expecting to get a row of zeros on this stuff every time. And when you do, write this as an equation with v1 and v2. v1 minus 3 halves v2 is equal to 0. Okay? So you end up getting v1 equals 3 halves v2, and v2 is free, so it's equal to v2. So you can write this as a 3 halves 1 times v2, and you've got your eigenvector for lambda equals 2. It is 3 halves 1. And for lambda equals 1, okay, you put it into the A minus lambda I, and you end up getting this matrix here, which will be 4 minus 1, which is 3, negative 3, 2, negative 2 when you plug it in. And when I reduce row echelon form this guy, I get 1, 1, 0, 0. Excuse me, 1, negative 1, 0, 0. Okay? And so this makes it even easier. When you plug it in your equation times your v1, v2 is equal to 0, 0. You end up getting v1 minus v2 equals 0, which means that v1 is equal to v2, and v2 is free, so he's equal to v2 free. So you get the vector 1, 1 times v2. There it is. The vector is 1, 1. Does that make sense? All right, now, the last two are pretty straightforward equations. What is the eigenspace? Get the word space on there. I mean, same thing as vector space, but you're using the eigenvectors. So what is that going to be? To be a space, you got to span the set of vectors. 1, 1, and 3 halves 1. Does that make sense? That's your eigenspace. It's the span of the eigenvectors. Okay, is this diagonalizable? Well, we had a major theorem. Again, memorize your major theorems. If you have distinct eigenvalues, then the eigenvectors will be linearly independent. What are my eigenvalues? 1 and 2. They are distinct. They're not the same thing. You don't have any double roots or anything like that. Double roots, you can have some issues. And I showed an example of that in class on our last lecture and stuff like that. That's not what I got here. So is this thing diagonalizable? The answer is yes. And I wrote, but why? Because there are two distinct eigenvalues. Lambda equals 1, lambda equals 2. There are no double roots on those eigenvalues. That's very much easier. You could have just said, well, I took this as a column matrix, reduced row echelon form, and I got a pivot for each column. Oh, I would have accepted that. I would have been ashamed of you, but I would have kept those points because working way too hard at this thing. Yeah. miss something? Which one?
Like eigenspace of A and dimension.
Oh, yeah, I didn't answer the question. Oh, yeah, I find the eigenspace of A and write the dimension. Okay, sorry about that, I was running ahead. What do you think the dimension is gonna be equal to? Oh, good, I'm correct, that's two vectors. Yeah, but you're right, I wasn't paying attention to that. All right. And then, what about this guy here? Well, I gave you the same matrix, so you've already got the eigenvectors and eigenvalues. I did that because I was trying to give a short test. Didn't matter, you guys are gonna hold off until the bitter end, holding on to these test questions in 15 minutes, even after the class is done, but that's okay. All right, so you got matrix A right here as 4, -3, 2, -1. You got eigenvalues of lambda equals 1 and lambda equals 2, and you got the associated eigenvectors of, what was it, 1, 1 for lambda equals 1, and it was what, 3/2 1 for lambda equals 2, okay? So is this thing diagonalizable? Yeah, D. And what will D look like if it's diagonalizable? You get the eigenvalues on the diagonal and zeros off diagonal, and this was a 2x2 matrix, so there's only 2 of these guys. So you end up getting, and order matters, but I like putting things in order, so 1 comes before 2. So this is 1, 0, 0, 2. That's how I wrote my answer to you, because it makes a difference. I could have put 2, 0, 0, 1 if I wanted to. But then, to get the P matrix, these are the eigenvectors in columns. So order matters. What was the eigenvector associated with lambda equals 1? It was 1, 1. What was the eigenvector associated with lambda equals 2? It was 3/2 1. So this would be your P matrix if this was your diagonal matrix. If you switched and made this 2, then this would have been 3/2 1, and if you put the 1 here, it would have been the 1, 1 on that side. Order matters. Does that make sense? So we were paying attention to this. Okay? So there it is. The answer is, and I'll write in both my answers, 0, 1, 0, 2, or you could have written 2, 0, 0, 1 if you wanted to, but then your P would have been what I just wrote, 1, 1, 3/2 1, or if you wrote it this way, it would have been 3/2 1, 1, 1. You just switched the columns. So I was paying attention to the order of what things turned into. But now, here's the point of this whole thing. What is A10? A to the 10th is the same thing as this P, D, P inverse. This is that being symmetric. Okay, we assume it being similar to D, similar to a diagonal, to the 10th power. So that's like popping this thing 10 times himself. But the P and the P inverses end up canceling, so this is equal to the same thing as P. The 10th power goes to the D times P inverse. So this is basically P, which is, I'm going to use this one, 1, 3/2 1, 1, times D, which is your 1, 0, 0, 2 raised to the 10th power, times P inverse, and I'll just write 1, 3/2 1, 1, with the little inverse symbol on that guy right there, okay? And then here was the trick. How do you power up a diagonal matrix? Basically, you take the entries on the diagonal and you just power those up. So this would be 1, 3/2 1, 1, times 1 to the 10th power, 0, 0, and 2 to the 10th power, times the inverse of this guy, which I actually put on my calculator. I end up getting -2, 3, 2, -2, and then all you got to do is multiply this guy out. Now remember, 1 to the 10th is just 1. 2 to the 10th power was 1024, and then multiply row by column. This is programming on the matrix calculator here, and you end up getting the answer of 3070, -3069, 2046, and a -2045. That's what your 8 to the 10th matrix ends up being. And of course, you check your calculator out to double check it, but this is the work we wanted to see. Does that make sense? Applying, the diagonalization really helps us with the matrix multiplication when you can make a matrix similar to a diagonal matrix and stuff, especially when you're trying to power this stuff up. All right. Yeah.
Why do you cross out the 1 to 10 to 10?
What's 1 to the 10th power? Okay, that's why I wrote the 1 there. What is 2 to the 10th power? 1,024, and then I can do row by column, and multiply the thing out. That's what you get for the answer. Okay? All right. Let's go back in time and look at test number 2. Oh, there it is right here, test number 2. We'll do this in reverse order here. Now, again, for these guys, hopefully you've had a chance to go back and go to the Math Learning Center if you made any mistakes, or at least come by and see me. Now, I just only brought version A here. But one of the things that's gonna be on your test, definitely, everything that I went over on that last test, was good. So study test number 3 and study all the problems in test number 3. That's gonna be, because that's the accumulation of all the stuff we've been working on. Now, let's talk about stuff like, from test number 2 material. All right? Taking the determinant of like a 3x3 matrix expansion by minors, you can expect to know how to do that type of thing here. Matrix multiplication and finding inverses of 2x2. And maybe something bigger, 3x3, but 2x2 is gonna be the classic formula. To do anything bigger than that, you take A and augment with the identity, you row reduce it, A turns into the identity, and the identity turns into A inverse. You may see something like that just to show you your work and stuff like that. But anything like this is good form, but don't expect too many questions like these because I'm trying to really focus on the major material. So matrix multiplication. This was a test that really focused on the determinants. So this was a good problem right here. Was basically how to take the determinant of something like this. And when I'm going to take a determinant, I'm going to do the expansion by minors, especially anything bigger than a 3x3 or bigger, I'm going to use the expansion by minors. But I'm always looking for the row or column of zeros. So what do you got here? What is your best dude? Second row. But don't forget you got to do your sign chart. You go plus, minus, plus, minus, plus, because this thing's got 1, 2, 3, 4, 5 on it. Then it's minus, plus, minus, plus, minus. And that right there is the row. I don't even have to do the rest of the sign chart here. And so you end up getting this 0 times somebody, who cares, plus 1 times, it's minus 0, plus, because that plus right there, 1 times, knock off the row and column of this thing, and you end up getting 4885, 4885. Okay, knock off the row and column with it, 6887. Okay, 0. Okay, row and column here, 0, 8, 3, 0. And knock off the row and column, and I end up getting 0, 2, 0, 0. Does that make sense? And then you play the game all over again, because the rest of them are going to be, I said, minus 0, plus 0, and those guys go away. So this guy now, I'm going to go after that last row, because that's the one that's got the most zeros in there. But this guy's 4 by 4, so this is plus, minus, plus, minus, minus, plus, minus, plus, plus, minus, plus, minus, minus, plus, minus, plus. And you notice that the plus shows up with the 2. So the rest of these guys are going to be, it's 1 times, this will be 2, it'll be a plus 2 times, knock off the row and column on this guy, you get 4, 8, 5, column here, 6, 8, 7, knock off the row and column, 8, 3, 0, excuse me, 0, 3, 0, 0, 3, 0. And again, I'm going to expand by this guy, so now I got 1 times 2 times, expand by this guy, this will be plus, minus, plus when you do your matrix here. That'll be a positive 3 times And then you finally get it down to your 2 by 2. 4, 5, 6, 7. Okay? And then you get, what is this, 6 times, 4 times 7 is 28, minus 3 times 5 is 30. I end up getting 6 times a negative 2. Oh, whoops, I lost the negative here. Where did I lose my negative? Oh. The negative somewhere. It should have been a negative 3. You're right. There should have been a minus 3 here. Why would this be a minus? Oh, because of that right there. I wasn't paying attention. It's a minus on the 3. Thank you. And so that would be negative 6 times a negative 2, which makes the answer 12. There you go. Just watch your signs and watch your careless errors. Does that make sense? Now, the other thing that I want you guys to pay attention to is doing something like reduce row echelon form on this stuff. Because of this guy here, do row reduction and then cofactor expansion. So what I was really after you guys doing would be something like this. I'm going to sweep down and make a bunch of zeros. Multiply negative 1 times row 1 added to row 2. Negative 1 times row 1 added to row 3. Negative 1 times row 1 added to row 4. You end up getting this. 1, 0, 0, 0, 1, 1, 1, 1, 1, 1, 2, 2, 1, 1, 2, 3. Okay? And then I'm going to do again, here's my question for you. Multiplying a row by a constant and adding it to another row, what does that do to my determinant? Nothing. The main thing's the same. So multiplying row by constant, adding another row, makes sure the matrix is the same. So I'm going to do a bunch of row stuff. As long as I'm multiplying a row by a constant does have an effect. Don't forget that. Swapping rows has this negative effect. Okay. So this one, okay, on this one, when you sweep down here, you end up getting 1, 1, 1, 1, 0, 1, 1, 1, 0, 0, 1, 1, 0, 0, 1, 2. And then I'm going to do one more move down here and knock off that guy. You end up, when you do that, when you do more reduced row echelon forming it, you get 1, 1, 1, 1, 0, 1, 1, 1, 0, 0, 1, 1, 0, 0, 1, 0, sorry, 1. I work real hard at this matrix here. So what do you end up getting there? All this. Do I need to sweep back up again? No. Once you have a diagonal matrix, whether it be a triangular matrix, excuse me. Once you have a triangular matrix, upper triangular or lower triangular, what is the determinant? The product of the diagonals. So the determinant of this thing is going to end up being 1 times 1 times 1 times 1. Yeah, let's not hurt ourselves answering this problem. So don't forget some of those techniques and stuff like that. And an application of, you can expect something small like this on your test, Kramer's rule. So go back and check Kramer's rule. And again, just to remind you, x is going to be equal to, you divide by the coefficient matrix, 3, negative 2, 1, 2. And for the numerator, replace the x with the constants of column 1, 7, 1, negative 2, 2. And y ends up becoming, the denominator is the same, which is a coefficient, 3, negative 2, 1, 2. But now replace the y's with the constant column, 7, 1, and the x stays the same, 1, 3. And you end up getting, take the determinant of these guys. You can expect to do something like that, just to remind you. This one is what I like, so you can anticipate something like this on the test, because it's quick. What is the, knowing that the determinant of A, B, C, D, E, F, G, H, I is equal to 12, what would the determinant of this guy be? Okay? So, here we go. In terms of this guy right here. See this? That entire row has a 3 being multiplied by it. You with me? So, I can pull out that 3, and that's left with D, E, F. Does that make sense? This is part of our, go back and look at your determinant properties here. When an entire row is being multiplied by a constant, you can factor that constant out and then just rewrite the row, and that's the effect. It'll be 3 times the determinant of this guy. This one has a 2 times A, B, C. So I can also factor out the 2, and I'm left with A, B, C. Now this guy right here, we did 2 times A plus G, 2 times B plus H, and 2 times C plus I. Multiplying a row by a constant and adding it to another row has no effect on the matrix whatsoever. So there's no effect, and you can just get the original. This is multiplying the constant times this and adding it to another row, no effect. This is the same thing as G, H, I. But you got one more move here. It looks like, remember the original matrix is A, B, C, D, E, F. We got D, E, F, A, B, C. So what do I have to do to get it back into this form? Swap rows, and when you swap rows, what do you have to put? A -1. So this will be 3 times 2 times -1 times the determinant of the A, B, C, D, E, F, H, I, H, G, H, I, G, H, I. But that happens to be 12. So the answer is 3 times 2 times -1 times 12, and you end up getting a -72 for your actual answer. Does that make sense? Questions? Just trying to remind you of some other stuff that we did, okay? Here's a gift. LU factorization of a matrix. Remember that stuff? Question first.
How did you get 12 when you were highlighting that number?
Oh, I gave you that. ABC, determinant ABC, D, E, F, G, H, I is equal to 12. So when I got this, at this point right here, I can replace that with just 12.
So how did you get the, that makes sense, so then how did you get the -1?
Because I had to swap rows. When I pulled the 3 out and pulled the 2 out, I got D, E, F, A, B, C. This matrix is A, B, C, D, E, F. So those rows have been swapped. And so if I swap them back, I got to throw a negative in there, -1. All right, this is why you guys come to these review sessions here. You remember that LU factorization? That was an awful thing we had in the test, but I want you guys to be able to do it, but not on my example. Not on example. Okay, so I'm not gonna make you solve the LU factorization on this thing. Now, from a computer science perspective, oh yeah, how many of you guys are computer science, computer engineering, or some kind of computer stuff? 95% of my class. You should pay attention to this LU factorization because it does require less steps involved, so your algorithm will save you some CPU time on this stuff. But at the end of the day, I'm not gonna put this guy on. Does that make sense? All right. In terms of these other ones, I will, on a few problems, because I know what the calculators can do, I will make you find, you know, an inverse or do some kind of reduced echelon form by hand by showing me the steps. Not many of them, maybe 1 or 2 problems at most, because we do have our calculator, but so pay attention to directions. You'll see, like in test number 3, I had a lot of questions about use your calculator to do this. And I'm gonna do the same thing on the test. However, there will be a couple of them where I want you to show your work on your, basically your reduced echelon form stuff. And I want you to signal it. 2 times row 1 added to row 2. Tell me what you're doing on that thing when you're doing it, so you can see it, because I know you can check it on your calculator. I want you to check it on your calculator, but I want you to show me that you understand the process, okay? So there's not gonna be many of those, maybe 1, yeah.
So in the final exam, obviously there's gonna be matrix, like there's gonna be like, the first couple of questions will probably be like, do the reduced row echelon formula.
Yeah,
right?
yeah.
So after we complete those, are we able to like within the rest of the test to maybe rely on our calculators a
Yeah,
bit more? So
yeah.
we can show that we know it in the beginning.
Exactly, and that's typically my goal here, just like we did in test 1. Test 1, if you remember test 1, I made you actually do the reduced echelon form a lot more. By test 2, I made you do it a couple of times, like this one here. What did I say? Show your work. So what you have to do here is you took B, augment it with the identity. You showed me the reduced echelon form, which was nice, it's 3 by 3, and I would do like this. But then this turns into the identity, and what you augment to actually turned into B inverse. Does that make sense? So it's something like this. Yeah, yes, ma'am.
So when you say show your work, that's the equivalent of writing out all the steps you did to get Mario?
Yes. Yeah, that's what I mean by show your work on this one. Otherwise, I'm gonna use those words I put on like test number 3. you can use your calculator to help you out with row reduction, yeah.
So for the final exam, you will specify we need to use like the calculator
Yes.
for the question, or if it's like, not like the main question is REF, but if you have to find something else, you specify for you and show it all over.
Right. I will be very specific. Like, for example, this one right here. Let's take a look at it. You got a system of equations. I wanted you to write it as a matrix. Now, that shouldn't have been too bad. You know, that would have been what? 1, 3, 8, 2, 4, 11, 1, 2, 5, times x1, x2, x3. It is equal to 12, 17, 8. Now, and look at this one. I gave you the inverse matrix. This is how I can save some time on this one. And so you have to be able to solve for x. Now, this is ax equals, we'll call that b right there. You with me? To get rid of a, you got to multiply a inverse on the left. So what you do on one side, you got to do on the other, but order matters. So x ends up becoming a inverse times b. The a inverse has to be on the left because a lot of people screwed up by putting it on the right because you weren't paying attention to the order. Because when you do this, if you got ax equals b, you got to multiply by a inverse because a times a inverse, they got to be right beside each other to cancel and get the identity x. If you put it on the right side, the x is in the way and you're not butted up beside each other. And so this, and what you do on one side, you do on the other, you get a inverse times b. That a inverse does not show up on the right side. It's got to be on the left because a is on the left. Okay? And again, make sure you know your definitions. Definition of a null space. I mean, this was test number 2, and I put the same definitions on test number 3 there. Okay? And of course, I do plan on doing something like this for you guys on the test question. Here's a matrix A, and Merry Christmas. I'll give you the REF, save some time, so you can just locate those darn pivots and stuff like that, and you can take this guy to help you basically step it up down the road about figuring out what the null space is going to be. If I gave you the REF, it's a lot easier to actually solve for the null space. Most of your time would be row reduction, row reducing it by hand anyway. So if I give you that, it saves a lot of time. Does that make sense? All right. Then, last but not least, let's take a look at test number 1. Test number 1, remember these words. You can anticipate, just as a good answer type thing, putting answer in parametric vectored form. I like these as in vectors. That's what we started out with. But remember, with systems of equations, there are 3 different types. What are the 3 different types of system of equations? Consistent, unique. What does that mean? There's one answer. x1 equals 5, x2 equals 7, and x3 equals negative 12. One answer. Consistent, infinite. What's that? Infinite number, you get those free variables. You get x1 equals 12 times x2 minus 3, or you get free variables in that thing when you solve for it. Does that make sense? And the last case is inconsistent. What is inconsistent, and how do you know? Got an equation, 0x plus 0y plus 0z equals 5. 0 equals 5, that can't happen. You know, inconsistent, all right? Okay, so anticipate something like that in terms of the 3 different types, okay? I do like a problem like this guy right here, where I make you figure out the values of h and k such that, and this also uses your ability to do reduced echelon form to make the thing, make sure it's consistent. So what you're doing is you're looking for a row of zeros when you row reduce it, and you're gonna get this 4th column over here, you're gonna get some kind of h and k equation. You gotta set, it's gotta be an entire row of zeros, otherwise it's inconsistent. You set that part equals 0, and you can talk about the relationship between h and k. Okay? This one, I do want you guys to focus on this one right here, number 4. Free points. Look at each one of these guys and tell me, is this guy in REF, or not in any kind of reduced echelon form type thing here? Okay? So, all right, so number 4 here, there it is right there. All right, what about this guy right here? This guy is this one? Well, notice the row of zeros is right here, but where is it not located at? It's not at the bottom. So this one is not in echelon form. Pay attention to the row of zeros. This one, you got the row of zeros on the bottom, right? And there's the pivot, there's a pivot, and there's a pivot. What do you notice about above and below the pivots? Zeros. That's RREF. What about this guy? All right, you got no row of zeros, but you've got your pivot here, pivot here. This is a pivot position, and this is a pivot position. But what you should notice here is all the pivots, they have zeros below it. Does that make sense? That is called REF. And pivots do not have to be ones in the REF. Only RREF do the pivots have to be ones. Does that make sense? So, one of these different kind here. In terms of this stuff here, go back and look at this, whether it belongs in the span. This was using the terminology and definitions here. I like giving problems like this, but I probably won't give too many in terms of this. So, because do it in three moves or something like that. I'm not going to probably do that to you guys. But does this belong to the span of this guy? Can you find an A and a B that you can multiply these two vectors by to give it to get this? So you go back and solve for it. That's a good question here. Basically, we talked about are these vectors linearly independent or not? So basically, I augment these guys and reduce row echelon form them. And if everybody's a pivot, every column, yes. And so the answer is either yes or no or something like this. The big question, I think, for most of them is, solving this, and I give you that RREF type thing here. State the definition of homogeneous. Absolutely, you need to know that. This one right here on, a lot of people, we went over this one in class, but the homogeneous equation, this was a particular a solution to the original equation equaling this guy here. And then for your answer, you take the homogeneous, which is the null space equation, add it to this answer right here, and it gives you your system of equations. And last but not least, on these stuff, we talked a little bit about linear transformations. Make sure you know your definitions of linear transformations and stuff, whether it is or is not a linear transformation. Usually it's not going to be something other because you have like a constant being added or something like that. Zeros have to map to zeros. That's your first choice. So state your properties of linear transformations. Make sure you know that, okay? But last but not least, I do plan on putting something like this on your test, just to see if you can write me a system of equations using circuits and stuff like that. I won't make you solve for it, I'll just make you write a system of equations. No, you got a copy of this. This is your test. Oh, the video? Well, I'm up to 1 minute, 1 hour, 17 minutes, so I'm after class now. So, but I will be uploading this guy to sometime after class. So study hard on this thing. I have been enjoyed being your professor this semester. Hopefully you decided linear algebra wasn't that bad. My big thing was how many of your colleagues wanted to borrow our videos from our class and stuff like that. So I got a lot more people registered with the class just so they can access the videos from this class, because I don't think the other guys are doing this. I got to talk to them about that. But study hard on this stuff. The final exam, study the old test is number one, and you will not be disappointed in what the final exam looks like. See you guys on Tuesday, December the 13th at 11 o'clock here. All right, bye.